So the next thing is you need to be very familiar and confident with the basic equipment that you use to do a titration. So you're going to do it in a conical flask. Okay, so this is different from the volumetric flask. This is where you're actually going to do the reaction, and if you have to draw the equipment, you remember to label it as a conical flask. And with the sort of experiments that we do at A-level, you're typically using volumes which, by the time you reach the end point, are about 50 cm cubed, because you'd be adding, say, 25 to 25-ish. And a sensible size of conical flask for that is 250 cm cubed. Anything smaller, and it'll be difficult to keep it mixed properly. Anything bigger and your solution gets too spread out and you can't see sort of colours and things clearly. It's also difficult to swirl. So again, specify the size of the equipment. That's important. So you've got a 250 cm cubed conical flask, and what you're going to do is to take one of your solutions and add it into that, and that's going to have to be an accurately measured volume. So the way you do that is you use a pipette. So a pipette is something that looks kind of like this. You've all done this in the lab. So remember, a pipette has a graduation line on the stem, just like the graduated flask, just like the volumetric flask did. And the idea is that if you've got your meniscus sitting there on the graduation line like that, that will be exactly whatever the volume on the pipette is. And typically, in most of the experiments you ever get to think about, that's a 25.0 cm cubed pipette. Okay, and so you pick up 25 cm cubed of solution in your pipette and you release it into your conical flask. What we're going to do then is add our second solution into that, and we don't know what volume is going to be needed for that. That's what we're going to look at for when we get the colour change or whatever it is we're looking for. And so what we do is deliver that from a bit of apparatus where we can measure what the volume is at exactly that point that we want, and that bit of equipment is called a burette. So again, you need to be able to draw it, so it's just a long tube like this with a tip on it like that, and crucially it has a valve on there which you can open and close, and that's a burette. So burettes are normally the ones that we use 50 cm cubed, so that means it will have graduations all the way down here, and it will have 0 at the top, and it will have 50 cm cubed at the bottom. And the idea is that you initially fill it up to somewhere near the top. It could be that you go to exactly 0, but it doesn't have to be. You just have to fill it up to somewhere near the top before you start, and then you write down what the volume reading is at the beginning. So here's your solution at the start, and you need to know what that initial volume reading is. So if you look in higher resolution at this scale, so you might have 0 here and 1 cm cubed there, and so on, 2, 3, 4, 5, and you get those markings in between. And again, you might well get a picture of one of these in an exam, and you need to be able to read off what the volume would be. So suppose your meniscus looks like this. Maybe a bit more symmetrical than that, so something like that. The question is, what does that read? Well, reading downwards, you can see that's 0.1, that's 0.2, that's 0.3. So the bottom of the meniscus, which is what we're going to read, is somewhere between 0.2 and 0.3. And the rule with burettes, and you absolutely need to know this, is that you read to the nearest 0.05. Okay, so you don't pretend that you can do better than that and look at that and say, oh, that looks a bit like 0.2 you know, that looks a bit like 0.2377 to me, because you can't read that accurately, not least because each drop that you release from the burette has a volume of about 0.05 cm cubed, so it's kind of meaningless to read it any more precisely than that. So you need to know that rule, that you always read to the nearest 0.05. So this one, what you've got to do is decide, is that closer to being 0.20 or 0.25 or 0.30, and the answer is, in that case, it's clearly closest to being 0.25. So that's what you would write down as your initial volume reading. If it was something more like this, okay, and you'd say, right, here's the bottom of the meniscus here, and you say, right, well, in this case, that's 0.5, 0.6, 0.7. It's slightly more than 0.7, but it's actually closer to 0.7 than it is to 0.75. So you would report that as 0.70, not just 0.7. Okay, because you're reporting that second decimal place to show that you have indeed obeyed the rules and read it to the nearest 0.05. So that one is closest to being on the 0.7 line. It's obviously not exactly on it, but that's the closest. So you say 0.70 for that one. So you write down your initial volume reading, and then you open the tap a bit and start releasing the solution. And as it goes into the flask, it's not going to mix properly unless you swirl it. Okay, so you must swirl, to mix as solution 2 is added. And you do that until you see, for example, the colour change, which, if it's an acid-base titration, you'll have an indicator in there, and you'll look for the colour change that tells you you've reached the neutral point. And so at that point, you'll have a new volume. So, it's going to be down here somewhere. And so you'll read off there and say, right, that's your final volume reading. And you just read it in the same kind of way as we did up here. And what you'll then do, and we'll look at this in the table in a minute, but the important idea is that the volume delivered, in other words, how much solution has actually ended up being added to that flask, is equal to the final reading minus the initial reading. And that's what you're going to do when you report your results in the table. And that volume delivered is sometimes called the titer. So if you see that word, it just means the actual volume required to reach the end point that you were aiming at, the colour change or whatever it was. When it comes to recording the results of a titration, there's a very sort of standard format that they like you to stick to, which is to set up a table like this, because the point in a titration is that you're almost always going to do it more than once. Because the more times you repeat it, the more reliable your answer is going to be. So you're going to set up a table like this, where you report the initial volume. Always put the unit down. Don't write the unit down next to each number, because apart from anything else that gets monumentally dull, but it's just good practice to write the unit next to the description of what you're measuring here, and then you just put the numbers down in the table. So initial volume / cm cubed, final volume / cm cubed. Quite often those are done the other way up, because when you do the subtraction, in the old days when you did it on paper rather than with a calculator, which you probably do today, it was just easier to sort of say this minus this gives this. So be ready for those to be sometimes the other way up. And then the titer, which, as I say, is final minus initial, so it'll be this minus that, gives you the titer. Now, when you're going to do repeated runs, the first one is generally going to be a trial. And you label it trial. And the idea of that is that if you've got no idea what the volume required to reach your colour change is going to be, it's quite difficult to get it exactly right, because if you add it, in the most accurate way possible, one drop at a time, it's going to take you forever potentially. If your actual answer is 32 cm cubed and you're adding it 0.05 at a time, it's going to take you forever to reach that. So what you do is you do the first one roughly, and you say, right, I'm going to add it fairly quickly so that I might well overshoot a little bit, but it doesn't matter because I'll know roughly where it is, and then in subsequent experiments I can home in on that and do it really precisely. So it's good practice to record a trial one, but it must be labelled trial, and what that means is that the result is not expected to be as precise as the other ones you measure, and so you don't include it when you calculate your mean titer later on. Okay, so you would do your trial titration fairly rapidly, just adding the stuff, swirling the flask around, watching for the colour change, and not being surprised if you overshoot slightly, because you're not adding it as slowly as you might do. So you might have an initial volume, you might have had it exactly on 0, but remember, you don't just write down 0, you write 0.00 to show that you've read it to the nearest 0.05. Your final volume might be, say, 27.80. So the titer is that minus that, which again is 27.80. They must always have these two decimal places, but the second one must be 0 or 5. So once you've done that, you can then just empty your flask, rinse it out with some water, and do your first precise experiment. So you can do this the same way, use the pipette to transfer the same volume of solution into your flask, but this time you know that you're aiming for somewhere roughly 27.8 cm cubed, but it might be a bit less. So what you could do is say, right, let's add the solution fairly quickly till we get down to, say, 27. So close to it, but definitely not there yet. So add it fairly quickly, swirling till you reach 27, and you should find, yeah, you haven't reached the neutral point yet. And then you switch to adding it one drop at a time. So drop, swirl, and after each swirl you look to see if the colour has changed. And that way you should be able to stop it at exactly the point where the colour changes. So that's the point of doing the trial, so that you only have to do that over a limited volume range. So you do that and you try and get it to the nearest drop, which would be to the nearest 0.05. So let's say this time that we started, with 5.30 as our initial volume reading, because you don't have to fill it all the way back up to the top. And let's say the final volume came out at 32.95. So you do the subtraction, 32.95 minus 5.3 is 27.65 would be our first accurate titer. And it's a little bit different from that, but let's say that's not surprising, because this one we weren't expecting to get it dead on. This one, that's what we're aiming to do. But we can't just assume that's right. So what you then do is you carry on doing experiments. So let's do another one. Repeat it in the same way. So let's say we started on 0.20, 0.20 this time, 2 decimal places always. So let's say this time this comes out at 27.70. So we do the subtraction, that minus that is 27.50. And so you say, okay, those two are quite close. Is that good enough? Do we just then take a mean of those two, or do we carry on? In real life, that can be a difficult thing to decide. What you're told is that you have to proceed until you get concordant titers. This word concordant means basically that they agree to a level of agreement that you're happy with. It's close enough, and knowing when it's close enough can be quite difficult. It depends how precise the number you need to get out needs to be, basically. That's not usually an issue that you have to worry too much about at A-level, but you might possibly in this case settle for that, but you might not. You might think, well, I want to try and get closer agreement than that, so you might do a third experiment. Okay. So let's say that this one starts on exactly 0 again, and this time you get 27.60. So you do the subtraction and you say, right, that's my third result. So now you can see that you've got three results that are really quite closely clustered. Remember, we're ignoring that one because we know that wasn't done as precisely, so you don't consider the trial at this point. But looking at experiments 1, 2 and 3, you and I might think, well, all three of those are, fairly close. 27.5, 27.6, 27.65. However, the exam board has a very strict policy on how you decide which ones to include in the mean and which ones to leave out on the grounds that they're further away and therefore are outliers, are not to be trusted because they don't seem to agree as closely as the other data. And their policy is simply that you just take the ones that are most closely clustered together and you ignore any other ones. So here you can see that this one and this one are 0.05 apart. This one is 0.1 away from that one, so the gap is bigger. So even though it's close, we say, yeah, that's not as close as these two. So you say those two are the closest clustered results, which means that we just take those two and we ignore this one and we say that the 27.50 was an outlier. And that means we don't include it in the mean. As I say, that might not be what you do in real life, because it's not very different, but that's the recipe that you learn for A-level. So it makes it easier because it means you don't have to make judgment calls, you just stick to the rules. So that means that our mean titer is the mean of those two. So it's 27.65 plus 27.60 divided by 2, which is 27.625. But again, we can't know it to that level of precision, so we could round that to 27.63 cm cubed is our mean titer. So that's the kind of presentation that you need to aim for if you have to construct a data table yourself, that you have all the units down there, it's very clear which measurement is which, the titrations are labelled clearly with the trial being distinguished from the other ones, and crucially all of the numbers have 2 decimal places, even if that decimal place is 0, as it often will be, because it's always going to be either 0 or 5. And that includes when you've done the subtraction, again 2 decimal places ending in 0 or 5. Learn the rule, you find the closest clustered of the accurate ones, leaving out the trial one, and you only take the mean of those closest clustered ones, you leave out any other ones. So we're just taking the mean of those two, and the mean should also be reported only to 2 decimal places. Let's just look at a couple more examples of finding a suitable mean. That's a common thing they'll ask you to do. A suitable mean means which numbers do you include and which ones do you leave out. So if you look at these ones, you can see those 2 titrations gave identical results. So although this one's also quite close, you ignore it, you treat it as an outlier. You say that those ones, because they're identical, are the most closely clustered ones, so you ignore that one and you say the mean is, well, obviously the mean of those 2 numbers is obviously that number, is 24.50 cm cubed. So here's a slightly less tightly clustered example, and this time we've got 4 numbers. So again, if we look at the pattern, these 2 and 0.15 cm cubed apart, and then if we look at this one on the end, that's also 0.15 away from here, but in the opposite direction. So you've got 3 readings there which are equally separated. This one, the one it's closest to is that one, but this time there's a difference of 0.2. So again, even though it doesn't seem all that different, for our purposes we say, right, that's an outlier, it's not as tightly clustered as the other ones, so we ignore that one. But the other three, because they're equally spaced, we have to use all of them, and we say that the mean titer is therefore the mean of those three numbers. So 22.80 plus 22.65 plus 22.95, all divided by 3, which obviously comes to 22.80 cm cubed. So that's a situation where you have more than two numbers which are equally spaced, and you have to, in that case, treat each of them as being concordant. But if you have any that are even slightly less closely pulled into the cluster, then you leave them out and treat them as outliers.